I am Ottorino Veneri, and I am the coordinator of an Erasmus Plus project that is called Internet of Energy. So today we have Dr. Calum McConnell that is presenting us one of the aspects of the Internet of Energy. In particular, is going to present a webinar titled Hydrogen's Role in Intelligent Grid Infrastructure. Calum McConnell is an expert. He is a managing director of ITM Power, which is a company located in Germany. So please, Dr. McConnell, you can start your presentation and you can share your PowerPoint to the people. Of course, at the end of this webinar, there is space for questions. So all the attendees are allowed to ask questions at the end of this webinar. So let's start, please. And enjoy this webinar.
So I hope you now see on your screens my slides.
Yes, we can see the screen, but you can use the presentation mode in order to have a better view of your slide.
Okay, so you should now see it in presentation mode.
Yes, yes, very nice.
Okay, so thank you very much for the invitation for today. I must disappoint everyone. I'm not a doctor. I'd love to be a doctor, but I'm not a doctor. And I'm the managing director of ITM based in Germany, but ITM is actually an English company. So it's a satellite location that I manage in Germany, and the main company and the manufacturing facilities are in the UK. So welcome to my world for the next 20 minutes or so. What I'd like to cover in today, and I'm going to be racing through some of the slides, so I apologize, but it's hopefully going to give you guys a nice overview about the technology, some of the reasons that the technology is useful, and its connection to grid usage, or connection to being used in the grid as a tool. So the agenda today: hydrogen, sector coupling, a little bit about the technology itself. It's a multi-tool, hydrogen and the grids, and an example of where the grids play a role is in the CO2 mobility, or CO2 free mobility. So first of all, set the scene for a couple of seconds. We all know that we have a CO2 issue that we all have to deal with on a global scale. And these three pictures kind of tell us why. We've seen where the CO2 emissions will go if we carry on doing everything the way we are today and don't change anything. And we can see on the graph on the left where we need the CO2 emissions to be if we are going to meet the goals set out for 2030 and 2050. One of the horrible things about the renewable energy world is the fact that CO2 is not just coming from electrical production. It's ignored by a lot of people, but you can see from the graph in the middle, the pie chart, that CO2 actually is emitted from a lot of different sources. So if we want to go CO2 free, we have a challenge across a lot of sectors or a lot of areas of the world that we live in. And power and energy is only about 21% at the time that this graph was made. So I don't claim that it's 2020, this graph I picked up in 2019 at some point, but it won't have changed significantly over the period. And the last graph is really just to indicate that the renewable energies that are coming onto the grid are growing. So the increase in volatility of electrical power in the grid is growing as we increase the number of solar and wind turbines that we have. So we've got to deal with that. And these challenges, they are connected through hydrogen. And that bottom picture, I'm going to explain a little bit more in a few seconds, but hydrogen in the middle kind of connects the areas of chemistry, heat, transport, fuel, renewable power. So what do we do as a company? ITM's business is the world of manufacturing manufacturing PEM, proton exchange membrane electrolysers. It doesn't have to be a container, but that picture just shows a container in the middle with a typical system in it. We are bringing the worlds of renewable power, water together, producing pure hydrogen and supplying it into many different areas. So it's about the systems in the middle. And these systems are changing as we go forward. The technology. This graph or this slide, I use it for many reasons. This is not about showing how great ITM is in its product development over the last years. This is about showing where the market is coming from and where it's going to. On the left-hand side, you can see in 2011, the ITM was selling a system which had about 40 kilowatts of electrical power, about 5 kilograms of hydrogen gas being produced in a 24-hour period if it was running at full blast. Over the next years, these systems grew slightly, and in the last 3 years, we are making a much, much bigger jump in system size, going from 40 kilowatts to something like 10 megawatts. That's 250 times bigger than we originally had in 2011. So in 9 years, we are making a product growth of 250 times, with all the challenges that go around that, from a factory able to produce small systems to a company needing to produce industrialized systems. Two examples of the product and give you an idea of what we're talking about when we talk about typical PEM electrolyzers on the market. On the top right-hand side of this slide, you see the core technology of my company, which is the stacks. The membranes in the layers, in the stacks, that are actually producing the hydrogen by separating water into H2 and O2. They are typically housed in containers or something similar. So the pictures, again, on the right-hand side, you see some of what one of these systems could typically look like. What I'd like to focus a little bit more heavily on, however, is the left-hand side. This system is about 1.3 megawatts of electrical power. So it can sink 1.3 megawatts of electrical power pretty quickly. And the figures that you can see toward the middle of the page, load control, cold start, and warm start, this system, if it's running, can go from 20% of its power to 100% of its power in 2 seconds. If it's not running and needs to run, but the system is warm, it can be at full speed in about 30 or more seconds, or just under, maybe about 35 seconds, running at full power. So you have an extremely flexible, fast load that you can be putting on your electrical grid and producing pure hydrogen. We'll come to what you do with the hydrogen in a second, but first of all, let's stay with the fact that it's fast. To give you an idea, again, that picture that showed that it was 250 times bigger, this is a CAD view of the plant we are building on a refinery in Germany. It's a 10 megawatt system based around modules. On the top right corner, you see the module going into a 5 pulled together stack system. And then that all being put together in a building and the balance of plant for water preparation and gas preparation around that core product. And this is not just about producing hydrogen in this system. This is about using this device as a flexible load and producing hydrogen. So the guys from Shell, and this is a funded project, they want to experiment with what one can do with this device when it's in an industrial space, in all of its aspects. So leading into the electrolyzer as a tool, but producing hydrogen is only a part of it. You can see from this picture, and I realize it's not that easy to read, especially probably on the end of a webcam, but you can see on the left-hand side, the system producing the hydrogen. In the middle, there are multiple little colored blobs. They represent process applications and the industries behind them. The message behind here is hydrogen flows into a lot of different areas. And it's all about what's on the right-hand side of that slide. It's about the mobility sector. It's about storing energy. So if you've got all the volatile energy coming onto the grid, this is a way to turn electrons into molecules, and then you can store the molecules. If you want to take the hydrogen back into electrical power by putting it through a fuel cell, then you have a source to do it with. Defossilizing fossil fuels. I smiled when I wrote that myself. This is about, and I look at the application in Shell, The refinery uses a massive amount of hydrogen already today that it's taking from steam methane reforming. So it's producing CO2 when it's taking CH4 and splitting it to get the hydrogen. We can defossilize some of the production of fuels and plastics by using green hydrogen instead of taking the hydrogen from CNG gas, hence defossilizing the fossil fuels. And it's, again, not about decarbonizing, because we quite often need the sea. It's just about not using the resource from the ground and putting CO2 into the air, hence defossilizing industry and defossilizing chemical production. Again, that's similar at the bottom of the page. It's about hydrogen in the middle and linking sectors. But they do more. The box on the left, you can see if you've got grid power and you have this extremely fast, flexible load, then you can start looking into things like grid balancing and frequency control. And this slide captures some of the ideas behind that. If I start from the right-hand side where you see the red and green graph, this is purely an indication of how fast the system reacts. So you see a power input going up and down, and the load of the electrolyzer following its signal. So it can dance up and down pretty much instantaneously as the power changes. Jumping down to the bottom of the slide where you can see frequency and, it's in German, last, so load. Let's imagine we have the 10 megawatt system that we have, or that we are building in the Shell refinery, and we run it at 5 megawatts. The Shell guys can offer a movable load of 5 megawatts from 5 to 10, or 3 megawatts from 5 down to 2, pretty much instantaneously to balance either their own grid or the grid off their refinery site. If they want to do frequency control, primary or secondary grid services, they can do it with this piece of equipment. So if I think about what this means, it's more than just producing hydrogen, hence the words on the left. It's a rapid response. So it's all about load management. It's a device that the grid operators should and could use, or could and should use. It's about smart operation. And by smart, I don't mean smart meters in our rooms or in our houses. I'm thinking about we need a holistic approach across the grid, electricity, gas, and other sectors. And the only way we'll get that communication is through digitalization. We need to be fast. We need to see what's going on. We will need intelligence across the grid. So we'll see these two areas of technology, in my opinion, growing hand in hand, because we won't be able to use these intelligently unless we can communicate with them intelligently. One of the things mentioned a lot is power to gas. I just wanted to give you an idea of why the hydrogen industry feels it's important, and we'll come back to grids in a second. This picture shows on the left-hand side the electrical grid, on the right-hand side the gas grid, and the electrolyzer being the device in the middle that connects the two. So you've either got electrical power to turn into the gas, or if you're talking about storing power, storing energy, you could also take the gas you've just produced, put it back through, for instance, a gas burning turbine, and turn it back into electrical power. At the bottom of that picture, you see CO2, either CO2 from the air, or you could take it from an industrial application, mix it with hydrogen you produce from the electrolyzer in the process of methanation, and you could feed the gas grid with methane. In some cases, you can feed the gas grid with hydrogen, so you could mix the two. I'm not personally, persuaded that that's the best way to go forward. I think that hydrogen is a gas that has far more use in its pure form rather than sticking it back and mixing it in with gas in a pipeline, but nevertheless, it can be done. So this picture is showing the dynamic between the two. And the words on the right, and bearing in mind what I said before, we will need to store energy. We won't get around the fact that we need to do that. And we know that electricity is difficult to store. So if we want to store renewable energy in large quantities, then we might want to think about using the gas network, whether it be in the form of hydrogen or in synthetic natural gas. And everyone who's spent a little bit more time thinking about this, their first thought will be that's really inefficient. I'm not denying that it's it's less efficient than using electrical power by itself. I don't think anyone will be. But I think we also have to face up to maybe efficiency is not the only thing that we have to bear in mind when we are talking about moving from where we are today into a fully renewable energy producing platform of tomorrow, with all the challenges that go with that. Maybe we have to take a drop in efficiency in some cases simply on board to manage the overall situation. So looking at power storage, one of the topics that's mentioned a lot in connection with hydrogen as well is, well, why do we need it? Why should we store it? And this graph quite nicely shows why the typical all-electric world scenario has some challenges. If you see on the left-hand side of that graph on the y-axis, the charging times or discharging times. And then on the x-axis, storage, that's not a linear scale. So please note it goes from 1 kilowatt hour to 100 terawatt hours. So it's more of an exponential scale. You can see that there is a space across that graph for all different sorts of storage technologies. And batteries have their limitations. Theoretically, they don't, but practically they do, because they become so expensive, they become prohibitive. If you look at the volume and the number of hours and the volume of storage that the power to gas, hydrogen, or the gas grid offers, one can get a conception of why that whole space about storing vast amount of energy can only really be done if we start talking about molecules. And the little picture on the right-hand side brings this home. If I look at the gas grid today in Europe, we have about 550 terawatt hours of stored energy and about 0.6 terawatt of electrical. That's today. I'm sure it'll change tomorrow. You can see, if we were thinking about an all-electric world, that red dot would have to get awfully large. And whether that's feasible, I doubt. But we will have multiple storage options, and we probably need a lot of them. So there's not one solution fits all. Last slide on hammering home the validity of using the gas grid is this. This shows basically a picture of how energy is interconnected across the different nations in the European space. And the fatness of the arrows indicates the energy content being transferred. So you can see at a glance, the red being electrical and the greeny blue being gas. The volume of energy that can be and is transferred between countries in the gas side of things is massive compared to the electrical lines. And to use one example, in Germany, we have about 3,500 kilometers backlog on making the north-south link of an electrical wiring to connect the north offshore wind to the south uptakers of the electrical power. And we already have a gas net in place that could do that. So one asks the question, why don't we use the infrastructure? An example of when the grids could be useful is e-mobility. E-mobility meaning electromotors being supplied by electrical power, not in the form of battery electric, but just electrical motors. There are two slides here which I think are very interesting. One, it shows that electrical power gets into vehicles and it takes time to do so. On the left-hand side of that picture, you can see the charging time in minutes. On the bottom of the graph, the X is the range in miles. So one can see the blue dots indicate batteries, the red dots indicate fuel cells. In a nutshell, you can get more energy into the vehicle in less time using hydrogen gas than you can with electrical power. And this is not an ITM graph. This is something that I stole, but it is quite nice to see. You can see the number of minutes it takes to charge these vehicles. It gets really interesting when you start thinking about the infrastructure behind it, and you can see a little bit about what I mean in the next slide. This is a slide with lots of numbers on it. Let's concentrate on the ones that highlight in red. First of all, this is a graph or a table showing the power levels or energy levels that a typical vehicle, a car, may have in it with petrol, diesel, methane, hydrogen, and batteries. And it's purely to indicate the type of energy in a vehicle. So the exact numbers are not precise, and it might not take exactly 4 minutes to fill a car with petrol, but you can see a dimension. And I said that If I want the batteries to compare with the hydrogen or the other vehicles, then I took an average car and thought, okay, 50 kilowatt hour battery and a 5 kilogram tank of hydrogen is a typical vehicle. So the energy on board in that red, 166 compared with 50 kilowatt hour. Time to fill it, all pretty much the same, between 4 and 6 minutes, or 6 minutes to fill that battery up. But in order to do that, you need something like the Porsche supercharger, 500 kilowatt hours, to get that amount of power into that battery in that amount of time, which is great if you happen to have a Porsche supercharger and your infrastructure network is able to carry a 0.5 megawatt of power. I could imagine if a whole car park of these things are lined up and everyone wants to charge the car in 6 minutes, we will have some challenges from an infrastructure perspective. So mobility is really about providing vehicles with energy. It's about the energy supply infrastructure, and it's about managing the infrastructure and its users. So we come back to, again, digitalization, smart technology, and smart usage. I couldn't resist this slide. For all those people that don't know, there are fuel cell vehicles out there. There are, and they go from small cars and scooters, things right up to buses, trains and boats, and everything in between. So it is the case that these vehicles do exist, and we should start entertaining the idea of using them to support the overall e-mobility drive. So in conclusion, and I'm pretty much on time, is the electrolyzer everyone thinks of today as a hydrogen producing device. I'd like for everyone to think of it as a tool that can join sectors, a tool that offers the potential to iron out volatility in the grid. It offers the potential to produce something we can store in an easy way. We can optimize our self-consumption of the power. You can optimize the use of a wind farm or a solar plant by doing that. We can shift energy from even one season to the next a lot easier with molecules than we can with electrons. Grid management, and it's a raw product provider for the chemical industry. So I hope that I've given you all a quick dive into the world of electrolyzers. And yeah, hopefully I've persuaded you that one can look at the electrolyzer as a tool and not just a production of hydrogen. Thank you very much for listening.
Thank you, Calum, for this interesting topic that you have covered with this webinar, which from my point of view was very interesting and gave us a better idea on the possibility of using hydrogen for many opportunities in many sectors, as you have shown during your presentation. So now it's time for questions. So some of the people who are attended this webinar have some questions for Calum McConnell.
I'm all ears.
Yeah, I have Clemente Cavastro speaking. I have just a curiosity. How many of these electrolyzers have you installed in Europe?
I just want to double check that I've understood acoustically your question. How many electrolyzers are there in Europe, or how many have I sold?
ITM electrolyzers are there in Europe? Roughly.
I would make a guesstimate. The majority of the product we have in the field is in the UK, because that's where ITM is based. There are quite a few projects there. So from the top to the bottom, we have 11 filling stations that we own and run. Most of them are in the London area. And look, in Germany, we have 4 systems at the moment up and running, or almost up and running. In France, we have a couple of systems. In the States, we have a system. In Scandinavia, we have a small system. So it is a very much growing, but we are a long way from being there as an industry. And there is more potential than actually what we have today to go get. I think one has to look at, again, that market. You see it from 2011 till now. a lot of the systems that we sold in the past were demo systems to universities or utilities looking at how to use the technology. As we go forward, when we look at the stuff that we have on our desks at the moment, there are a lot of large companies asking for large systems. So I don't think it will be about the number of systems, it will be about the size of the systems and what one does with these systems as you go forward.
Okay, thank you very much. I see that in the chat there is also another question from Christian, who is asking, are there any issues for this kind of systems?
Are there any what, sorry?
Any safety issues from this kind of system?
Sorry, just a second. Sorry, Calum, can you show your camera? Can you switch on your camera so the people can look at you when you are explaining these questions?
Do you see me?
No, not see you.
My camera is on.
Yeah, that is not important anyway.
Okay, so my camera is showing that it's working. So
yes.
Now
so
are there any
issues? Are there any issues?
Yes.
Safety issues. Safety issues.
So, yes, there. I think you have to be fair. Yes, there are some challenges. I'm not sure issues is the right word, but there are challenges. The biggest challenge is probably the regulatory marketplace that we operate in. So most of the time when we are wanting to take electrical power from the grid and be useful as a tool, like I've just presented, then we are penalized by the grid operator or by the power prices, that when we actually turn on the devices and produce hydrogen, the hydrogen itself becomes quite expensive based on the price of electricity. So the regulatory framework that we all have doesn't tend to recognize this device as something to be used on the grids, which is useful for the grid operators today. So one of the things that is a strong requirement in Germany is to look at how that framework can be changed to allow this whole thing to take shape. That would be the biggest single concern I have. But to be fair, from a technology perspective, we have a lot of customers asking for guarantees, saying, well, can you guarantee the product will do what you say it will do in 10 years from now? And it's a really difficult question for the manufacturers at this moment in time to answer with 100% correctness, because you saw on that one of the graph slides or the pictures, 10 years ago, we were making products that were probably even more than 250 times smaller than the market is requiring today, with a completely different technological base. The PEM membrane wasn't even the same membrane as we now have today. We were operating at different amps per centimeter level. We had different manufacturing technology in place. So this market is requiring us to move at such a rapid speed. It's difficult to therefore rely on your technology of 5 years ago and say, yeah, that will be the same in 5 years in the future. So you have your 10-year lifespan. That's probably the second biggest challenge that we all have to face up to, that the technology is moving fast. I hope that answers are there issues? Yes, there are some that we need to take on board.
Okay, any other questions from the people who has attended the webinar? Actually, I have a sort of curiosity, perhaps it's a stupid curiosity, but anyway, perhaps it's also related to the question that was already done. But what is the reason to use the PEM technology? Is just a reason of safety, just a reason that the electrolyzer can be realized with other technologies that are used for fuel cell, for example?
No, not at all. I think there are some very valid selling points to using the PEM technology compared to the alkali technology, which tend to be the size, so the compact nature of the product. we have a higher current density on the membranes than alkali products do, which in itself means you can put more electrical power in and get more gas out on a smaller footprint. So if you need the area, the physical area of these devices to be smaller, then PEM has a good, let's say, good lead on that. We don't use any other chemicals. We don't produce any byproducts. So our byproduct is water. Our raw product is water, and the main product is hydrogen or oxygen. So from a chemical perspective, it's a lot easier to deal with. One of the things that's being talked about is the PEM technology tends to be more expensive than the alkali technology, which is about 120 years old. I would say, yeah, I would agree. The PEM technology is, however, on a cost degradation trajectory, which is far steeper than the alkali technology. And we expect it as the volumes grow, and one is heavily dependent on the other. We won't get the costs of this product down unless we start producing more volumes. So I think of the mobile phones when they first came on the market, they cost a fortune, and now we have almost Einstein clever computers in our back pockets, which cost nothing and are a lot smaller and a lot more efficient. It will be the same with this technology. We need to produce it en masse. We need to get supply chains which are a lot more lean than they are today. We need to stop building systems which are all custom made, and every single design is different from the one before it. So we need to standardize our products, which is one of the reasons ITM has gone the way it has gone over the past period. So if you put that all in a bag and say, what are the advantages? I think if you're looking at the medium term, you'll see PEM doing the same as alkali from a cost perspective. It's smaller, it's more reactive, it doesn't produce chemicals. You can exchange, if you need to, exchange the membranes and the stacks a lot more easily. Put it all together, I think there is a good business case for using PEM technology rather than the alkali. And obviously, am I biased? Yes, of course I am. I work for ITM and we produce PEM technology.
Okay, thank you. Very interesting. Any other questions from the attendees? So thank you, Calum McConnell. I hope that this webinar was interesting for all the people who has attended the webinar. I think so. That also hydrogen and electrolyzer have a big impact in the future. We know very well in our sector the transportation system. I have seen many electrical vehicles powered by fuel cell. It means that hydrogen can be a vector, an energy vector of the future. I understand that the infrastructure is not easy to build immediately, so it takes time, but I think that it's a very good perspective to manage the energy in the future. So thank you again for your availability to make this webinar. All the people perhaps already know, but it's better to repeat that this webinar will be available on our website, the website of the Internet of Energy Erasmus Plus project. So you can see again this webinar, and please join our Facebook page where you can have some links also to this webinar and the other webinar were part of this project. Thank you again to everybody.
Okay. Thank you very much for inviting me. Have a nice afternoon and stay healthy.
Okay, thank you.
Bye-bye.
Bye-bye, thank you.